Okay, welcome to lecture. We'll get started here in just a second. Like usual, if you do have any questions, feel free to ask them down there in the chat box and we'll get to your questions. So we're picking up here at, I want to say 19, I think this is it. So at the end of chapter 19 here where we sort of left off last week. And I think we're right about here in terms of this slide. So again, we'll get started here in just a second. Okay, so we have been talking about sort of complex ions, coordination compounds. Again, a reminder, as we talked about last week, a coordination compound can almost be thought of as like an ionic compound. There's really a positive guy or a cation, if you want to think about it that way, and sort of a negative ion as well. And again, the coordination compound consists of two things. It consists of a complex ion, which can either be positive or negatively charged. And it also consists of a counter ion, which will also either be positive or negatively charged. And again, a coordination compound essentially is sort of like an ionic compound in the sense the positives and the negatives will balance each other out and have no charge usually overall. But again, the complex ion part will either be positive or negative. And that's also important, as we also talked about, which was naming these complex ions and coordination compounds. And when we go to name these guys, again, depending on whether or not the complex ion is positive or negative as to how we sort of name it. Again, if it's a negative complex ion part in a coordination compound, we use sort of the older school name of ways of naming the elements. So again, something like iron would be ferrate, something like copper would be cuprate, and we sort of use that sort of older way where they end in ATE. If the complex ion part is positive, then we use just a regular name for the metal, which again would be like iron or copper. We always include a Roman numeral for the metal that's in the complex ion part. Excuse me. To indicate the charge on the complex ion, not charge on the metal that's in the complex ion. And again, that's very similar to sort of type 2 nomenclature with transition metals. But here again, regardless of the metal, we always sort of use the Roman numeral to indicate the charge. Remember that some of the ligands that are attached have some special names that we went through on those lists. And also, again, we talked about coordination number. And coordination number, again, is not how many ligands there are in the formula, but it's dependent on the particular type of ligand. Again, the ligand could be monodentate, which means it binds in one place per molecule. It could be bidentate, which means it binds in 2 places per molecule. Or it could be polydentate, which means it binds in multiple places per molecule. So we saw EDTA, for example, which binds in 6 different places per every one of those molecules. So if you have something that's a bidentate ligand that's involved in a formula, again, the coordination number will not be necessarily how many you have of them. So for example, if you have something like oxalate, oxalate binds 2 places per oxalate molecule. So if you had 2 oxalate molecules in a compound, then the coordination number there would be 4, 2 for each of them. Again, the coordination number is how many atoms are directly bound to the metal in the complex ion. Any questions on any of that stuff that we talked about up until this point? And again, if you do have questions, feel free to ask them as we go through. Even if we've sort of moved off of that page, we'll go back and make sure we do it. So the next thing we're going to sort of talk about here is isomers. And the general definition of an isomer is essentially something that has the same sort of molecular form, if you will, but they do have different properties. And there's several different types of isomers, which we're going to kind of get into just a little bit here, not very, very much in depth, but we're just going to kind of touch upon these things. As you can see here on this diagram, we have structural isomers, and those have different bonds, and that's basically different ways that they're sort of put together, if you will. There could be a coordination isomer, and we'll talk about what that is in just a sec, and a linkage isomer. On the other side of sort of this little chart here, we see that there's also what are sometimes referred to as stereoisomers. And if you take organic, you'll learn all about isomers and very, very much in depth. But stereoisomers basically have the same bonds, but different sort of arrangements in three-dimensional space. And there's ones that are referred to as geometric isomers, which are cis and trans, and we'll talk about what that means. And there's also optical isomers. Optical isomers have the ability to sort of turn plain polarized light. So we're going to talk about a little bit, again, we're not going to go into a tremendous amount of detail on these isomers, but just to kind of touch upon this topic here. So the first type of isomer we're going to talk about is, again, what is referred to as a coordination isomer. And these are two coordination isomers here. And these are both obviously coordination compounds. And just like before here in the bracket is typically your complex ion. And in this case, the Br would be our counter ion. While down here, if we look at it, this part here is our complex ion part. And over here would be our counter ion. And what we see if we just sort of count up everything, if you will, in terms of the formula, you know, there's one chromium in each, there's 5 NH3s, there's a sulfate in each, and a Br in each of them. So they both have basically the same formula, if you will. But this difference here between them in terms of coordination isomers is, in the case of the top one, the Br minus is a counter ion, which means it's not part of the complex ion. So in the top one, what we have is a chromium, and just kind of, we basically have our NH3s. And we also have our sulfate. And those guys there are part of our complex ion, which, you know, would have an overall charge of +1. And as we sort of talked about last time there, the Br minus is there really just to balance out the charge. So the Br minus, again, not part of the actual complex ion in the first part, but still there as a counter ion. As in, that's different than the bottom one, which also still has our 5 NH3s. And what it has, though, is the Br actually attached to the complex ion part. Again, here, the overall charge on this guy would actually be +2. And our sulfate here would be on the outside as our, again, counter ion in this particular case. So although they both contain the exact same elements, the exact same amount of everybody, the way that they're sort of connected is different. In the top one, again, the sulfate is actually part of the complex ion, while in the second one, obviously, it is not. We also talked about a couple of things as well here. You can see that obviously this is a +3 charge. Again, that's the way it would all balance out. This is also still a +3 charge here. And that's why in the top case, the complex ion part was an overall charge of +1 from the +3 and -2, while on the bottom one, the overall charge on the complex ion part was actually +2, because directly attached to the chromium is only that -1, and that gives us a +2. Now, another type of isomer is a linkage isomer. And in a linkage isomer, much like the name implies, it's actually how the ligand is attached to the complex, to the metal in the complex ion. Now, what we have here is basically the same ligand. So in our picture over here, what we have going is NO2- as our ligand. Now on NO2 minus, both the O and the N have the ability to attach, although each one will only attach to one place. And in the first case here in part A of the picture, what we see is the linkage that happens between our NO2 minus, our ligand, and the cobalt is actually through the lone pairs on the nitrogen. While in the second case, in part B, we have really the same ligand, again in both cases, the exact same ligand here. It is just the linkage point on that ligand. In the second case, it is the oxygen that is attaching as opposed to the nitrogen that's attaching in the top one. And again, they obviously would all still have the same sort of formula, if you will. But again, because this ligand has the ability to either link in, if you will, through the oxygen or the nitrogen, we get these two different isomers that can develop. And it's really just based on the actual ligand and how it attaches to the metal. Now we're going to talk about some other sort of isomers, and these are sometimes referred to as stereoisomers. And stereoisomers can be geometric isomers, which is the first thing we're going to talk about. And we're talking about cis and trans isomers. And in general, cis and trans isomers, you come across a lot in organic chemistry as well. But in general, what cis and trans means is cis means basically same side, and trans means opposite sides. So in sort of a traditional organic cis and trans isomer, a lot of times that arises from when they have double bonds involved, or alkenes. And when we talk about cis or trans, sometimes in organic chemistry, it again means basically a lot of times the same side of the double bond, for example, or the opposite side of the double bond. But here is sort of orientation in three-dimensional space, which is sometimes where you get cis and trans, also in organic chemistry, which is alkanes. But basically the same atoms and the same bonds there are, but they have different bond angles. And they're very common in square planar sort of geometries. If you remember, square planar is sort of our octahedral arrangement as one of the geometries that we see, where basically all four atoms are basically within a plane of a square. And that's what we see here, right? All four atoms are basically within the same plane of a square. And we have the cis and the trans isomers, again, of these complex ions. And the cis here is on top, and we see that the NH3s are on the same side, if you will, or even the Cls are on the same side. And the trans here, what we see in sort of three-dimensional space is we have sort of opposite sides there of the square, if you will. And we have our trans isomer that occurs. Again, you can see they both have the exact same formula, which is what makes them isomers. But really the main difference here is sort of the orientation of those ligands that are attached. So again, our groups sort of all line up on the same side of the metal here within the plane. And again, that gives us our cis, while we have our guys line up on opposite sides, which gives us our trans. Here's another sort of example as well. We have the trans isomer of this complex ion and the cis isomer there in B. And our sort of trans part of it, if you want to think about it here, is our chlorine. Again, remember that this is almost all within the same plane, if you will. And again, this is sort of above the plane, and this guy is below the plane, which would be on opposite sides of the plane here. This is obviously slightly different than what we were looking at here. Here, the coordination number is 4, right? So coordination number is 4. Here, the coordination number is 6. So in this coordination number of 6, we get sort of that opposite arrangement happening. And here, what we look at on the right-hand side, you can see the two chlorines have now sort of moved to the same side of the plane, if you will. So they're both kind of on the same side here and here. And that would, again, be our cis arrangement. Now, sometimes these things are very hard to sort of visualize on paper, if you will. But can do your best. Again, we're not going to probably get too far into any of those type of things, so you don't have to worry about too much in terms of probably drawing any of these things or anything like that. Optical isomers are isomers that basically have an effect on plane polarized light. And also when we talk about sort of isomers and organic chemistry type things as well, you sometimes come across these ideas of what are known as chiral or achiral. A chiral molecule typically means that you have sort of 4 different groups attached to it. And usually what it means really is it has a non-superimposable mirror image. So if you have a chiral compound, its mirror image is non-superimposable, while different than if you have something that's what is referred to as an achiral compound. Achiral means it does have a superimposable mirror image. The isomers are also sometimes referred to as enantiomers. And again, chiral meaning basically that if you take the mirror image out of the mirror and you rotate it around as much as you like or move it around as much as you like, you'll never be able to get the mirror image to fit perfect over the original sort of image, if you will. And a very common thing of that is like your hands, as we'll see in just a second. But here again is a plain polarized light. You have a light source, goes through a polarizing filter, and you get guys going on sort of both directions here. And you could also measure, obviously, when it goes through the sample, that angle of sort of rotation. Also, how we sort of get things like D or L sort of isomers that occur as well. D being things are on the right-hand side, L meaning left. But this sort of is a very good sort of example of a chiral sort of situation. Again, if you put your hand up in front of a mirror, the image that you'll see coming back to you is basically your left hand. For example, put your right hand, you see your left hand coming out. Now, when you pull out that mirror image, like they kind of did there on the left-hand side, you could rotate that around as much as you like, but you'll never get it to fit perfectly on top of your right hand. You can do that with your left hand if you want. You can rotate it as much as you like. You'll never get it to fit perfectly on your right hand. You can get the thumbs to be on the right side, the correct side, but the problem is one hand will have palm up and one hand will have the palm down, right? So they're not technically perfectly the same. You could go palm down on both hands, but then your thumbs will be on the wrong side, and obviously that wouldn't fit either. So a chiral molecule, basically that is sort of what it means. If you take the mirror image out of the mirror, you do some rotation, again, you will not be able to perfectly match up the original image with the mirror image. They won't fit perfectly. Even if you try to rotate it, you try to twist it, turn it, flip it, whatever you like to do, they will never be able to sit perfectly on each other. There's always something that is sort of wrong, if you will. There's always some group or ligand in this case that is sort of out of place where it shouldn't be. So here's a couple of examples. And again, some of these things are a little hard to visualize, but here is our isomer. There are mirror images. And the mirror image is, these mirror images cannot be superimposed. So there's no way you can take out the mirror image. So what they did is, this is the mirror image right here. They took it out, and that gives us this guy over here on the right. And you can rotate it as much as you like, but the problem is really, if you kind of really analyze this, they will never fit right, because here, the original end-to-end sort of bond is here. But in the mirror image, that bond gets sort of moved all the way back here. So as you keep rotating, say, this guy around, that nitrogen there will really not connect in the right spot anymore. And again, they would be chiral molecules of each other. So just that slight difference because of the mirror image that basically happens. You get that sort of difference in connections. And just to kind of, let's see here. So basically, if you want to kind of see how they get that mirror image, again, you know, this guy comes to there, this guy basically goes to the back, right? And then that guy comes here and so forth. So that's how you sort of get these guys in the wrong sort of locations, if you will, as it sort of gets reflected back in the mirror. Now here, when we look at this, the trans isomer and its mirror images are identical, which is what's happening in part A here. So again, when these get reflected, this guy's going to come close, this guy is going to come back, this guy comes close, this guy goes back. And what it do, though, if you pull out that mirror image, as you can see, it pretty much matches, and they will be superimposable. So that is not a chiral molecule because they are superimposable. And so that would be more like an achiral. Here again is the one that we sort of saw a second ago. When we pull that out, we do get that non-superimposable mirror images. So we can't even have the exact same sort of compound, if you will. And the difference between the sort of the trans and the cis is here, we will get the non-superimposable image happening in the cis isomer and not so much here in the trans isomer because of the way the linkages are. So enantiomers are basically two molecules that are mirror images of each other, and they are non-superimposable. So again, that is what basically an enantiomer is, sort of a chiral molecule and its mirror image that basically will not superimpose on each other. A lot of biomolecules are chiral. A lot of drugs are as well. Sometimes only one of these sort of isomers are effective in curing a disease. All right. Any questions on isomers? Again, you won't be asked probably to draw any of those things. At most, maybe you'll have a picture. You have to recognize it as either, you know, what type of isomer it is. All right, so we're going to finish up here talking about sort of electrons and how they're sort of put into sort of a complex ion and how the bonding sort of works and what they end up with in terms of paired electrons and unpaired electrons. So when we talk about electrons, right, there's some types of bonding and so forth that we've talked about previously, or you've talked about previously. The formation of a hybrid orbital, for example, right, sp, sp2, sp3, again, from sharing of electrons. The Vesper model, which is sort of that molecular geometry that you learned when you did regular Lewis structures, doesn't work very well for sort of complex ions. So we sort of view sort of the interactions of the ligands and sort of the metal as more of an acid-base reaction. Again, more of that Lewis acid and base sort of reaction where we're donating electrons and sort of accepting of electrons. And the hybridization that sort of occurs does depend on the number of ligands that are basically attached. So here's sp3d2, and that is basically the hybridization that sort of occurs when we sort of visualize a complex ion that has a coordination number of 6, if you will, right? sp3d2, if you just add up, that's 1, 3 more make 4, 2 more make 6, yeah? And that sort of is what we envision here with something like this here, where we have a coordination number of 6. And you can see here, this is sort of what we envision happening. Our cobalt, which is positively charged, sort of the deficient in electrons. And here our Lewis base donating electrons in to these d orbitals of the metal here, right? Some other hybridizations, sp3, right? If you count up sp3, that is 4. So that's a coordination number of 4 is where we see that, right? We have sp2d. That is also usually a coordination number of 4. That is, again, your sort of square planar geometry. And we also have sp hybridization, sp being 2 letters basically, right? So that is probably your coordination number of 2 that sort of fall into that category. So again, here's some prettier pictures of the coordination number and sort of the structure that we visualize with these complex ions. And again, it's sort of similar to the geometry that you learned as well. Again, basically 2 electron pairs, 2 bonds is your linear geometry. Your 4 electron pairs, right? 4 bonds is tetrahedral. And your 6 electron pairs, really, right? And 6 bonds is sort of an octahedral sort of structure. Again, square planar, which we see as sort of an exception to the octet rule, also though falls with a coordination number of 4, as essentially in that case you have those non-bonding electrons involved as well. Now, when we talk about our d electrons or our d orbitals, and usually that is what we're talking about when we talk about sort of complex ions, as for the most part, right, a lot of those guys are transition metals. And transition metals, right, typically begin right there at the 3D. And on the periodic table, the transition metals are our D block, if you will, in terms of electron configuration. And as you remember, hopefully there are 5 different d orbitals pictured here on the screen. We have our dz squared, or dx squared, y squared, dxy, dyz, and dxz. Now, in the absence of a ligand and in just the metal by itself, all these d orbitals are pretty much equal in energy. So in the absence of a ligand, your 5 sort of d orbitals, badly drawn equally, are all equal in terms of energy. And if you remember, when we just basically think about electrons, right, and how electrons go into an atom, right, they go in basically one at a time, right, up, down, right, up, 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 down, down, and so forth, right? And they always basically fill the atom in the lowest energy level to the highest, if you will. So they start at the lowest. If the lowest gets filled, then they go to the next lowest, and then that one gets filled to go to the next lowest. So obviously in the absence of a ligand, if all the d orbitals are perfectly equal in energy, they would fill these d electrons or d orbitals like you would envision, again, one at a time, and then come back basically and start pairing it up. Now, what actually happens though, once ligands sort of get involved or are near, there's actually a shift in terms of the energy of the actual d orbitals within that metal that's going to be in the complex ion. And that's going to affect, obviously, the way that the electrons basically will go into that particular atom, or how the electrons fill those different d orbitals. So again, on the left there, in the absence of the transition metal, we have our normal, everybody's the same, we're going to come through, we're going to fill, and so forth. Now, what happens, for example, in a octahedral arrangement, sort of coordination number 6, is you actually get this splitting of those d orbitals. So these are our 5 d orbitals that we just saw. And you actually get splitting of them where 2 of those d orbitals actually end up higher in energy than the 3 other d orbitals. And when we go to sort of distribute the electrons for the metal in that case, it is going to affect how those electrons basically go into sort of the atom. Now, the difference between the sort of higher d orbitals and the lower d orbitals, the energy difference there between them is what is known as the crystal field splitting. And the crystal field splitting is sometimes abbreviated with the delta symbol. You could calculate it, as you'll see, just like you've calculated energy in the past by using really the energy equation there. E equals h times the frequency, h being Planck's constant, that's 6.63 times 10 to the minus 34, c being the speed of light, and obviously lambda being the wavelength. And that's the energy difference that occurs. So as we'll see, sometimes this energy difference between sort of the higher d orbitals and the lower d orbitals is not all that much. So when electrons come in, they're just going to come in like normal. They'll go in one at a time, and they'll lower guys first. And then they'll go, well, that doesn't look too bad in terms of that energy difference. And they'll feel like normal, you know, kind of coming back through and filling them. Now, in certain cases, though, the split of those orbitals is large enough to actually make a difference in terms of how the electrons basically will go in there. And what will happen sometimes is they'll start to feel like normal. And when they get to the end, they'll go, that looks pretty big, that big jump from the lower guys to the higher guys. And they'll go like, never mind, we're just going to stay down here. And they'll actually start pairing up these lower ones first before they're sort of forced to come up there. And depending on the sort of that crystal field splitting difference, it's going to result in a certain type of complex ion, either going to be referred to basically as high spin or low spin, as we'll see. And high spin essentially means that you have a lot of unpaired electrons, while something like low spin means you have a lot more paired electrons. Remember, paired electrons is what we see on the bottom there, arrows heading in one way and the other, right? So this right here would represent a paired spin, right? Remember that in terms of the quantum number, that's the ms is equal to plus a half, right? This guy would be the m sub s would equal minus a half in terms of, say, its quantum number. So paired spin means that obviously unpaired is like what we got up here. So you can just see the difference between what I just drew and previously drew. This one here has less unpaired electrons, would be considered more of a low spin situation, while the first one where they all just kind of went up in order, will get you a lot more unpaired electrons. Any questions on that? Oops. So as I mentioned before, the reason this could all sort of happen and electrons can kind of get promoted up there is, again, these are close in energy, right? Those d orbitals. And when we do something like absorption and measure absorption, we always want to look for sort of the maximum wavelength. And the maximum wavelength is where we sort of see this peak. So sometimes when you do some type of spectrophotometry, where you want to set it to the proper wavelength, you usually will do something like this, or somebody has done it before in the past, where they measure different wavelengths in the absorption values. And again, you usually want to set your wavelength on your machine to sort of your maximum wavelength. And what that ensures is essentially in your particular experiment that if you run an experiment, all your values will be basically on the curve, basically. So you'll be able to get values. Again, if really your maximum wavelengths is what I circled over here, and you decide I'm just going to set my wavelength way over here, you will only get things to give you absorbance values of a very, very small amount, and most of them will be off of the scale in that case. So again, that's why we usually will find that maximum wavelength to set things to. Now, as I mentioned earlier a second ago, again, this is the equation. It really is to figure out the crystal field splitting. And it is really the same energy equation that you learned in Chem 50 and maybe before that as well. And again, these are a couple versions of it. Again, H is our Planck's constant, which is at 6.63 times 10 to the minus 34 joule seconds. C is the speed of light, right? The 3 times 10 to the 8 meters per second. And again, wavelength is your lambda, right? And then obviously the new here is your frequency, right? So much like sort of a traditional sort of energy calculation there, if you know the wavelength, of light, you can actually figure out the energy of that crystal field splitting. Again, if you know the frequency as well, it'll allow you to figure that out. So let's take a look at an example here, and I think on your notes it's worked out. So let's just kind of go through the calculation here to just make sure everybody's on the same page. So if we were given the absorption maximum of this complex ion here occurs at 470 nanometers, what is the color of the complex and what is the crystal field splitting? So the first thing though, as you may know, or maybe you don't, but just to make sure, what we actually see in terms of color is the complementary color to the wavelength that's being absorbed. So the wavelength that's being absorbed, we actually will see sort of that complementary color to it. So in this particular case, the maximum absorption is 470, which puts it right here in the bluish color. And this sort of color wheel here shows us that the complementary color, if you will, to blue is orange. So when we look at the solution, we will actually see an orange solution. And that's often why sometimes people are confused when they are told to sort of set the wavelength to a certain wavelength in nanometers. And they're like, well, I'm setting it to blue, but my solution is orange. And again, that's because what's going to be absorbed is the complementary color to what we actually see. So if you had a red solution, for example, you would want to set the wavelength somewhere in here for a green area, again, because that's the color is going to be absorbed, and that's why, again, we see the solution that is red in color. So again, when we set the wavelength, when we do any type of experiment, we actually set it to sort of the complementary color in terms of the wavelength to what is being absorbed. If we wanted to figure out the crystal field splitting energy in kilojoules per mole, and we're only given the wavelength, we would use that wavelength and basically the energy equation that we just saw here. And again, sometimes crystal field splitting is abbreviated by that delta symbol by itself. And we would take H, which is a constant, so that's Planck's constant. C is also a constant, which is the 3 × 10⁸. And we obviously unit-wise need to convert our nanometers into meters. So nano is 10 to the -9, so that gives us 470 × 10 to the -9. That gives us this amount of energy per atom, and we want it though per mole. And that's why here we use basically Avogadro's number to go from joules per atom to joules per mole. The atoms will cancel each other out, and you'll be left with joules per mole. And then you could obviously divide it by 1,000 to get to kilojoules per mole. Any question on that calculation there? So a couple of main things. The calculation part hopefully should be very similar to what you did there in Chem 50. And the color part, though, is something maybe people don't realize. Again, we see the complementary color to the wavelength that's being absorbed. So how do you know if sort of this splitting of these d orbitals are going to be a big split or sort of a small split? And what will help you determine that is this right here, what is on the screen, which is the spectrochemical series. And it's basically a series of different ligands that you could have in a complex ion. And some are what are referred to as weak field ligands, and some are what are referred to as strong field ligands. So on the left-hand side, we have our weak field. On the right-hand side, we have our strong field. And basically, if it's a weak field ligand that's present, that means that the difference here for our crystal field is going to be small, which means the electrons will typically go in like normal, one at a time, and then come back and fill, as the difference between sort of the lower d orbitals and the higher d orbitals is not that big. Now, if you have more of a strong field, like one of those guys on the right-hand side there, that also, again, will affect how those electrons go in, we're going to get a larger split between those d orbitals, which means the electrons will go this way. And again, when they get to the end, they're going to decide that's way too big to go to the top. I'm just going to fill down here first. Again, as I mentioned, until maybe they're forced to have to go up at that point. And again, this is going to give you more paired electrons on the right-hand side there with our strong field, while we'll have more unpaired electrons typically with our weak field. And these will again arise two types of situations. You'll get what is sometimes again referred to as high spin complex. And again, in a high spin complex, you have more unpaired electrons. While you'll have a low spin complex, which in that case, you will have more paired electrons. So you may ask, what's the deal in the middle? Well, the deal in the middle is they will oftentimes give you some information as to how to maybe draw the arrows in the boxes. They may say, hey, do it with water with a low spin, or do it with water as a high spin complex. So they'll usually, for those guys sort of in the middle in the problem, give you some piece of information as to sort of how to distribute those electrons as either maybe high spin, low spin. They may say do it as a strong field or weak field ligand. So kind of those guys in the middle-ish, you know, they'll kind of give you sort of that some information about it. If not, you could kind of go whichever way is leaning towards the strong field or the weak field, but usually somewhere in the middle, especially like water and stuff like that, they'll sometimes give you some information. Now, they may not give you information in certain cases, and that's because there are certain cases that it doesn't make a difference. And what I mean by that is you could do it as, say, a weak field ligand, and you could do it as a strong field ligand, and you'll actually end up with the same distribution of electrons, regardless of sort of which way you did it. And there are certain things that do end up that way. So if you come across something where they really don't give you information about, you know, high spin, low spin, it may just be a situation where regardless of sort of which way you do it, you'll end up with sort of the same sort of outcome. And a very common question that you're asking these type of questions or problems is basically just that, how many unpaired electrons would this complex ion have? So that's a very common sort of question that's asked. Now, what we're actually looking at in terms of this particular splitting that we've been seeing here is that octahedral splitting, and really is that coordination number of 6 here is basically what we're looking at. So here are two sort of examples of iron complex ions. And just to walk through how we get to sort of that distribution of electrons in each of these cases, let us talk about that. So first off, right, it really starts with iron and its electron configuration. So if you just take iron with no charge, you're looking at an electron configuration of argon 4s2, 3d6. Now, when iron becomes +3 in terms of its charge, as we talked about before, the first electrons that are lost are our s's, right? And that's 2 electrons. Then we need to lose one of the electrons there, and that gets us to an electron configuration of argon 3d5. So these 5d electrons are these guys over here, yeah? So that's where those 5 electrons basically come from, right? And in this sort of complex ion here, the iron is +3, obviously. This is -1, and again, that's how come it's a -6 overall. So when we look at this iron here, this coordination number is 6. So the splitting that we're going to see is this exact splitting here, right, with the coordination number 6. The other thing that we want to look at is F. And again here, F is leaning towards more of the small filled, small separation there, our weak filled. So what that means, when these 5 electrons are distributed here in the iron, we have 1, 2, 3. Then it's going to go, that difference between these two guys here is not that much. So we're going to distribute our electrons like normal. And what we end up with in this particular case is 5 unpaired electrons. And that is why this is referred to as a high spin complex. Again, we have more unpaired electrons. Now, when we look at the complex ion on the right, the iron with the 6 cyanides attached, again here the iron is going to be +3 as well. Coordination number again on both of these are 6. And that again means that we're going to have our same splitting that we see here with our XY, YZ, XZ on the bottom, our squared guys up on top. But when we look at CN as our ligand in this case, that means we're going to get a strong field that's going to be there. And what that means is when these electrons come in, they're going to fill 1, 2, 3 electrons and decide that is too big. Yeah. So it much rather come back and put the 4th electron and the 5th electron on the lower energy level because of the energy differences there. And as you can see, what you end up with in this situation is we end up with only 1 unpaired electron. And that means that this is what is considered a low spin situation. Any questions on that there? Let me see here real quick. All right. So why don't we do, let's see. Why don't you try one just to make sure. Why don't we do this guy here, cobalt, right? There we go. So we have this. All right. And why don't you do this, and why don't you draw the arrows and figure out how many unpaired electrons it would have. All right, so why don't you take a minute or two and sort of draw a little diagram for that and figure out how many unpaired electrons it would have. And we'll talk about it in just a second, see how it comes out. Okay, so let us take a look here. So we're looking at cobalt and this complex ion. So we know that this is 0. So we do know here we're talking about cobalt with a +3 charge. So when we look at cobalt with no charge, we're looking at argon 4s2 and 3d7. So cobalt here with a +3 charge. Again, we're going to get rid of those and one of those, and that's going to leave us argon 3d6. So we really have 6 electrons to distribute here. And since the coordination number here is 6, that's our octahedral arrangement. So it is going to be this splitting where we do have our bottom guys are, XY, YZ, XZ, and our top guys here being our squares. And really, we want to figure out what's going to happen here. So if we look at NH3 and we back it up here, NH3 is here, and could kind of sometimes go both ways, but we'll lean it towards strong here. And we'll do both actually just to show it to you, but probably more of a strong in this case. So what that means is if we do this for a strong field, that means that we want to distribute these 6 electrons, and they would go in 1, 2, 3. Now the strong field here means that it's going to be a big difference between the lower and upper, which means those electrons are actually going to end up pairing off instead. And you're going to end up with 0 unpaired electrons in this case. Any questions on that? So again, probably a little bit more towards strong field. And again, just to show you the difference here, if for some reason you came across a question, they said don't do it for strong field, but do it for weak field for the exact same guy. And again, sometimes they may specifically tell you to do it one way or the other. If we did more of a weak field for this guy, we would end up with 1, 2, 3. Weak field means this is not so big, 4, 5, and 6 electrons. And we would actually end up with 4 unpaired electrons in this case. Obviously more high spin over here, right? And this would be more low spin, obviously, right? Any questions on how to do that? Again, if you weren't told one way or the other, probably could lean towards the strong field in this case, again, because it's closer to that side. Any questions on how to distribute those electrons or figure out high spin, low spin? You do need to know how to do that, again, for octahedral splitting here. And here's just an arrangement of all that. So on the left-hand side, we have high spin. So these would all be a result of a weak field ligand, again, going to allow us to sort of distribute those electrons like normal, one at a time. While on the right-hand side, we have a lot more low spin for different sort of numbers of d electrons. And again, this would be a result of a strong field ligand. Again, the difference here between the lower and the upper d orbitals is greater. That's going to allow them to want to pair off first in the lower ones before they sort of journey upwards to the upper d orbitals. So this again is your octahedral complexes, your coordination numbers really of 6. Yeah. Yeah, I would think your question is if there was water, for example, and didn't specify which one to do, weak or strong field. So like I said, there's really probably 2 ways that you would come across a question. If it didn't necessarily specify, again, like I said, sometimes they won't specify, And it's really because regardless of sort of which way you do it, you'll end up with the same outcome. And that occurs sometimes where it doesn't really matter sort of which way it occurs. Either if you do it high spin or weak spin, you'll end up with the same number of unpaired electrons. Everything will sort of be the same. And in certain cases like that, they won't tell you that. So that usually will mean that you could probably choose either one and it will probably come out the same. Secondly, they most likely, if it does sort of make a difference, they definitely will give you some type of information in the problem. Like I said, they'll either say do it for a weak or strong field, or they'll sometimes just tell you to do it as either a high spin complex or a low spin complex. And they'll give you sort of that piece of information. And again, if they obviously tell you high spin complex, that usually means that it's weak field. And if it's low spin complex, it usually means it's a strong field and so forth. So like I said, they'll usually give you some piece of information if it's somebody sort of in the middle, and even like something like NH3, which is sort of off middle a little bit as well. A lot of times they'll give you that information. But if they really don't give you any information, you probably could do it either way, and it would obviously come out kind of the same, regardless of which way you do it. Other questions on that? Now, what we're going to look at here is some other splitting of these d orbitals. So remember what we were sort of looking at specifically a minute ago, and in sort of all those examples, was your octahedral splitting. And again, that's more of your coordination number of 6. Here we're at tetrahedral, which again drops us to a coordination number of 4. And what we see is a similar splitting pattern, except that it's opposite of our octahedral. So our XY, YZ, and XZ orbitals end up higher in energy than our kind of squared orbitals, if you will, end up on the bottom. Works the same way if it's weak field, they're going to feel like this. Again, one at a time, and then come back and bounce. If it's strong field, they will fill up those bottom guys first, and then come back and pair these guys. So it works kind of the same way. They'll fill these guys up, and then they'll proceed upwards as well. So for tetrahedral complexes, this is again coordination number of 4. sp3 hybridization, you'll get this splitting pattern here. Again, works the same way as the one we were talking about with octahedral. If it's weak field, we're going to fill everybody like normal. If it's strong field, then we are going to kind of pair up first. So you do need to know for this one as well, coordination number of 4, tetrahedral splitting. Now square planar, which is also coordination number of 4. You can see a little bit different in the splitting. So you got some stuff going all over the place here. So same idea here. We'll get, if it's a strong field, we're going to get everybody to pair up a little bit lower before they sort of move up. And if it's weak field, they'll move down. So for us, I think you don't have to worry about this one, so I'll put a big X. Don't worry about this one. But you will need to know this one, which is our tetrahedral, and you will need to know, obviously, our octahedral. Yeah, so those are the 2 that you'll be responsible for here. Coordination number 6, octahedral splitting, and tetrahedral splitting, coordination number 4 in terms of these. You need to be able to draw these boxes, if you will, or lines in the arrows. And distribute the electrons accordingly. You'll need to know, obviously, the spectrochemical series there in terms of the ligands. The one you don't need to know is the very last one, which is the square planar one, which is kind of the weird splitting of all those orbitals. So you'll need to be able to obviously know the little ligand sort of chart. You need to be able to draw the arrows in the boxes. And like I said, a very, very common question is how many unpaired electrons you get, either it being high spin or low spin. Any questions on that stuff there? So again, this one here with the X, you don't need to know. All right, so that should wrap up chapter 19. That it is. All right, we're going to go off to, we're actually going to skip the next chapter, which is 20. We're going to come back to that one. We're going to go to 21, which is nuclear chemistry next, and the notes should be up online as well. So just give me a second here to get it going. All right, got that. Got that. Okay, so like I said, we're going to kind of jump a chapter to 21, and then probably next week we'll go back to 20, which is organic. We'll talk a little bit about whatever we got left at that point. And that's it pretty much. So we're getting into the final 2 chapters here, right? So 21 is nuclear chemistry. So we're going to talk obviously about nuclear reactions and how they're different and similar to, whoops, come back. Similar obviously to traditional chemical reactions, and obviously how they are different. So let's talk a little bit about radioactivity. Radioactive sort of nucleuses, they pretty much will spontaneously basically decompose into smaller nucleuses. They basically are said to be going through what is referred to as radioactive decay. Anything that basically will go through that is obviously unstable. And when it goes through sort of that decomposition to form a smaller nucleus or a new nucleus, it obviously emits a lot of times particles and a lot of energy. And the one main difference, as we'll talk about in this chapter, definitely between sort of a traditional chemical reaction and a nuclear reaction is in a chemical reaction, what we're essentially dealing with is electrons. We're dealing with electrons, we're dealing with bonding, breaking of bonds, and that's all basically the electrons, which if you think about the atom, are on the outside of the atom, obviously. Now, different in sort of a nuclear reaction or sort of a nuclear process, if you will, what we're doing is actually a lot of times starting with one element and ending up with another. And if you remember, the main thing that helps you determine what element you're talking about is the number of protons. So really what we're changing here when we do a lot of nuclear reactions is the actual nucleus. And that involves our protons, that involves our neutrons. And obviously when we start changing elements and changing protons, those are subatomic particles, and we definitely need a lot of energy to do those type of things. So when we start out with sort of a nuclide, which is sometimes what is referred to as a radioactive nucleus, is sometimes referred to as a nuclide. That is sometimes what is referred to as the parent nucleus, and that is undergoing the decay. And what it basically ends up at when it maybe hits something that's more stable or more stable nucleus is what is sometimes referred to as the daughter nuclide. So the parent is sort of where it starts, the daughter is sort of where it ends. And if you look on the periodic table, anything above sort of 84 protons is typically radioactive, and that usually will bring you towards the very bottom row up there on the periodic table, where you have your actinides sort of hanging out. That's where a lot of those guys are. Those 2 rows on the bottom of the periodic table, the Lanthanides and actinides, those are typically radioactive sort of elements, if you will, and where a lot of them are found. When we talk about a lot of nuclear reactions, they involve a lot of different types of particles, and three common particles that our good friend Rutherford sort of discovered. We remember Rutherford, he did something with some gold foil, right, and some alpha particles. He just sort of helped discover the nature of an atom and sort of the makeup of it. And alpha particles, which are abbreviated with the alpha symbol, have a charge of +2 and a mass of 4. And they're basically known as sort of the helium nucleus. And in in nuclear chemistry, I guess that's a better way of saying it, you'll sometimes see the alpha symbol, but one of two ways. Obviously, the alpha symbol and a 4 and a 2. Or you'll sometimes see just helium written to be used to represent an alpha particle. So very common in nuclear reactions, an alpha particle will be displayed as sort of helium with the 4 and the 2. A beta particle or beta ray basically has a -1, and it's basically an electron. And it also has a couple of symbols commonly seen. The beta symbol, obviously with a 0 and a -1. And because it sort of represents like an electron, people will sometimes just use like the E sort of symbol to represent that it's an electron sort of particle, also with the 0 and -1. Gamma rays, that is basically just pure energy. And if we remember perhaps from Chem 50 as well, that electromagnetic spectrum at the very, very, very end of that spectrum typically is where you find gamma rays, past X-rays and so forth. Gamma rays means that it then has a very small wavelength. And if you remember, wavelengths, right, correspond to energy. So super small wavelength, very high in energy, right? So it's like pure radiation basically. And it actually oftentimes will just use sort of the gamma symbol. It actually has 0 and 0 in terms of the numbers that are associated with it. There's some other sort of particles that we'll see commonly used in nuclear reactions. Another one is what is referred to as a positron. And oddly, that is a positively charged electron. It has a better attitude, I guess, than a regular electron. Thank you very much. Here twice a week. It also will use the same symbols as we see here for the beta particles. It will actually use the beta symbol, but it will have the +1, or it will sometimes be represented the same way, but it will show that +1. So if you, for example, see just the beta symbol like that with nothing else written, it's probably safe to assume that it is a beta particle. Usually if they write the beta particle and they want it to be a positron, they'll put something with a plus there. So sometimes you'll see that to indicate that. Again, if you don't really sort of see anything written, you could probably safely assume that it's a beta particle. Sometimes unstable nuclei will undergo what is referred to as an electron capture, and that pretty much is what it sounds like. It grabs onto an electron, basically. So there's a couple of words that you sometimes come across in nuclear chemistry that's important. So in terms of placement of particles, and when we talk about placement of particles, we talk about equations shortly. And basically nuclear equations sort of set up similar to a regular equation. There's an arrow. It's kind of where it stops in terms of similarity almost. But when we talk about something being emitted or goes through this type of decay, usually what that means, if it's emitted, emission follows this sort of decay process, usually what that means is the particle will end up on the product side. Now, if we see something where it says in words, like we see at the very bottom, an electron capture, you bombarded a nucleus with some type of particle. So bombarding, electron capture, that usually means if you have to write the equation, the particle will be on the reactant side. So this is like bombarding, electron capture. On the product side, this is more like emission or emitted, something's emitted, some type of particles emitted, and that's sort of how you know what sort of which side of the arrow to put these symbols. And this brings up two important things when we write sort of these symbols, and that is the atomic number and that is the mass number. And the atomic number is the number of protons that you find in a nucleus of an atom. And that is sometimes abbreviated with a Z. And that is found on the periodic table. So that is the number that you find above the symbol on the periodic table. Now, the mass number is the number of protons and the number of neutrons that you find in an atom. And that is not found on the periodic table. So just a reminder that when you look at the periodic table, something like hydrogen, this is the atomic number, which is your number of protons. This number on the bottom is not your mass number. This is your atomic mass, not the mass number. And hopefully you remember that when you calculate the mass number, the atomic number, number of protons, number of electrons, number of neutrons, those all should really be positive whole numbers. So if you look on the periodic table, the atomic mass is definitely not whole numbers for most elements. So again, not the atomic, not the mass number on the periodic table, only the atomic number. Why that's important is because if you take the mass number minus the atomic number, that will tell you the number of neutrons there are. So if you take the mass number minus the atomic number, that gets you your number of neutrons. When we typically write these symbols with the mass number and the atomic number in them, mass number usually goes top left of the symbol, atomic number goes bottom left of the symbol there. And remember, everybody has protons, electrons, and neutrons, except for hydrogen has just a proton and an electron, no neutrons. So this little table down here, again, is some other common symbols, some of which we've talked about. A couple other ones here that's also seen a lot in sort of nuclear equations is a proton. So a proton, again, is represented one of two ways, either with the P, for proton, where the mass number is 1 and the atomic number is 1 as well. Or sometimes people will just use the hydrogen to represent a proton, and that's why it's also sometimes called a proton. A neutron is another common symbol that we see in nuclear reactions, and a neutron is symbolized by an N with a 1 and a 0. And then here's the rest of the ones that we sort of talked about. An electron, which is also a beta particle. Our positron, which, as you can see, uses the same symbols, but again, one is -1 and one is +1. And our alpha particle over there with our helium and our alpha symbol. So it's important that you know these symbols. More importantly as well, obviously, is you know the mass number and atomic number associated with these particles, because again, that's going to be very important in sort of balancing nuclear equations, which we'll talk about here shortly. Now, in terms of these different types of particles that are radioactive, they do penetrate further. Whoa, sound effects, I like it. Not sure if you could hear the sound effects, but they do penetrate further, for example, into, say, a piece of lead or even into your tissue. You can see that the alpha particles don't penetrate as far as, say, the beta particles. They definitely penetrate a lot further, and gamma rays penetrate even further. And when you use some type of radioactive sort of substance, if you happen to do any type of research with it or just working with it, you know, in the course of your job, for example, it's always good to know what type of emitter it is. Yeah, is it an alpha, beta, gamma? What type of particles are coming off? because of the type of particles that are coming up, it requires different levels of protection. And as you can see, if you're dealing with something that's a gamma emitter, you need a lot of protection, like some lead and maybe some shields and all kinds of stuff. While if it's something like an alpha emitter, perhaps you don't need as much sort of personal protective equipment there while you're working with it. Obviously, you always want to make sure you're wearing the proper equipment, and obviously, most importantly as well is time. Not being exposed to it for a super long period of time is also very obviously helpful to not have bad things happen. Here's just another table of the different symbols that we've talked about. So let's talk about actually how to balance nuclear equations. And it's a lot more difficult, if you will, than a traditional chemical equation. I'm just kidding. Actually, it's not. It's like way simpler than balancing a regular chemical equation. So again, a major difference, as we sort of touched upon, between a traditional chemical reaction and a nuclear reaction is, in a traditional chemical reaction, we have that conservation of the elements. And what I mean by that is, obviously, when you balance an equation in a chemical equation, you change the coefficients. And basically your goal is to end up with, on the reactant side and the product side, the exact same number of elements, right? And that means if you started with 6 carbons on the left-hand side of the arrow, you should have 6 carbons on the right-hand side of the arrow. They may just be in a different sort of compound, but you still have the same number of each element on each side. And when we do a nuclear reaction, we do not have that conservation of those elements. We actually make new elements, right? And that means that you cannot balance a nuclear equation sort of like you traditionally would balance a chemical equation with coefficients. So what we do when we balance a nuclear equation is there's really 2 things that needs to happen for it to be a balanced nuclear equation. And they revolve around the mass number and the atomic number. So basically, when you go to balance a nuclear equation, in order for you to have a balanced nuclear equation, what you have to make sure is when you add up all the mass numbers on the left-hand side. So here we have 235 and 1 gives us a grand total of 236 for the mass number on the left-hand side. When we add up the mass numbers here, we have 138, 96, and the coefficient 2 times 1 gives us 2 here. And when you add up all that together, that is 236. So that is balanced in terms of the mass number. The same thing needs to happen for your atomic number, which again is the bottom left number. So when you add up all the atomic numbers on the left-hand side, here we have 92 and 0, gives us 92 total on the left. Coming here on the right-hand side, we have 55, as you can see there, 37, and 2 times 0 is 0, which gives us 92 on the right-hand side. And this would represent a balanced nuclear equation. So it looks a little bit different than obviously a chemical reaction or equation. We obviously don't have conservation of elements, which is definitely what you don't get here in nuclear reactions because we're changing to new elements. But we do have sort of the conservation of the mass number and the atomic number. So sometimes in these equations, you will be missing something. So for example, here, let's just say that this guy was not there. Right? And they're like, can you find the missing sort of element that's going to be formed? And what you really want to do when you do these problems is have a periodic table handy. It's your friend. And really the number that's going to help us determine sort of what element's missing is the atomic number. Remember that the atomic number is the number of protons, and it's the number of protons that determines the element that you have. Again, if you look on the periodic table, the atomic number is on the periodic table, and there is no atomic number that repeats, which means every single element has its own unique atomic number. So really the atomic number is the thing that's going to help you determine, what is missing. So the approach that you would want to take is you would want to add up the atomic number on the left, which in our case would be 92. And then on the right-hand side of the arrow, you would have 37 plus 0, which would be 37. And basically, if you took 92 minus 37 in this case, that should get you 55. You then would go to the periodic table, and you would find number 55 that's on the periodic table. And when you would go to the periodic table, you would see cesium. And that's how we know that that would be the missing element in this particular case. And again, the atomic number would go on the bottom. And then at that point, what you do is the same thing for the mass number. Again, on this example, 236 is what you got on the left. And over on the right, we have 96 plus 2, which gives us 98. And if we take 236 minus 98, that's going to give us 138 as our mass number. So sometimes you'll be given sort of these equations where something's missing, and you need to determine sort of the missing element. Good place to start, again, is with the atomic number, and then work your way to the mass number. Now, for the most part, a lot of times it will be an element that you find on the periodic table. But remember that something missing may not necessarily be an element per se. It could be something like a neutron. It could be something like a proton. So if you get to something, a proton, you'll probably be able to figure out as hydrogen anyways. But, it could be something like a neutron or, an alpha particle or something like that. So, I would say 9 times out of 10 is probably going to be an element, but it could technically be missing a particle, which is why it's important to know those particles and also the charges, or not charges, but the mass number and atomic number that goes with it. So why don't you take a second here and write the balanced nuclear equation for this guy here. That is PO212. It decays through alpha emission. So write the completed balanced equation. So take a minute or so and we'll talk about it. And then we'll probably be done for lecture here. Okay, so let's take a look here. So PO decays through alpha emission. So a periodic table, it's helpful. So we have PO as 212. And again, the periodic table is going to be helpful for a couple of reasons. First off, we want to find PO and find where it's at. And looks like the atomic number is 84, again, on the periodic table. Now, it decays through alpha emission. So the couple of words are important. Obviously, alpha is our alpha particle, which you could use that, or you could use the helium. And emission means that that particle will be on the product side. So again, here you can use the helium, or you could use the alpha symbol in this particular case. So again, the missing new element is going to come from our atomic number. So on the left-hand side, we have 84. On the right-hand side, we have 2. So again, if we take 84 minus 2, that's going to give us 82 as our missing atomic number. Again, you want to go back to the periodic table and you see number 82 is lead. Now for our mass number, we want to do the same thing. On the left-hand side, we have 212. On the right-hand side, we have 4. So 212 minus 4, 208 we'll go with, and 208. So this would represent our balanced nuclear reaction. Again, it's balanced because when we go to the left-hand side, the total mass number is 212. When we go on the right-hand side, 208 and 4 is 212. Left-hand side, 84. Right-hand side, 2 and 82 is 84. So really, again, like I said, the periodic table really is your friend when you're doing this sort of thing. Any questions on that there? Okay, we'll stop here for lecture today. Couple of reminders. I believe Thursday we have an exam coming up. So we'll do it like normal. We'll do a little bit of a lecture on Thursday. We'll continue on this chapter to keep us on pace. We'll take a break, and then during lab time, you could take your exam. In terms of labs, I think scheduled for today is the electrochemistry experiment, which is up as well. So you could continue to work on that experiment as well. I think I'll open up the lab section for a little bit. If you do have questions, you're welcome to come by and ask. If not, then obviously use your time wisely and make sure that you are working on these experiments as they will be due. And if I'm not mistaken, 1 week from today during lab, 1 week from today, we will be doing the project presentation. So hopefully you're working on that as well, because I believe that is next Tuesday those start. I believe the lab lectures should be up there, if I'm not mistaken. Everything should be up there. I'll double check, but they've been up there for a bit, so I'll double check though, but I think they should be up there. Homework for chapters 20 and 21. Yeah, I think there will be, I don't know how to put it. Let me think. For 21, there is, I believe. And for 20, you probably don't have to worry too much about 20. It's organic chemistry. So we're just going to kind of delve a little bit into it. I don't know if I'm going to collect 20 and 21's homework, to be truthfully honest with you. I'll probably just give you the points if you take the final. But I would recommend you do homework from those chapters because it will be on the final. But I don't know if I'll have you upload it or not. So I think you probably did. Okay, I'll double check. Then maybe I accidentally did. So I'll double check it if it's the same recording or not. Thank you for letting me know. I'll double check in just a second after we're done here and hopefully get the right one up there. Any other questions? Okay, so again, we're not starting any new labs or anything like that. You should be continuing on with what's up there. If you do have questions, you feel free to come by. I'll be there for a bit in lab. If not, like I said, I'll see you Thursday for lecture first. and then exam. Okay. Have a good rest of your day, and I'll go double check on that recording right now.